Let's check audio. Waiting for YouTube. Okay, we can start listening.
What's strange about that last number is that you might expect it to be more like halfway between 50% and 100%, since 22.5 degrees is halfway between 0 and 45, but 85% is significantly higher. To see concretely how strange this is, let's look at a particular arrangement of our three filters. A, oriented vertically, B, oriented 22.5 degrees from vertical, and C, oriented 45 degrees from vertical. We're going to compare just how many photons get blocked when B isn't there with how many get blocked when B is there. When B is not there, half of those passing through A get blocked at C. That is, filter C makes the lamp look half as bright as it would with just filter A. But once you insert B, 85% of those passing through A pass through B, which means 15% are blocked at B. And 15% of those that pass through B are blocked at C. But how on earth does blocking 15% twice add up to the 50% blocked if B isn't there? Well, it doesn't, which is why the lamp looks a lot brighter when you insert filter B. But it really makes you wonder how the universe is deciding which photons to let through and which ones to block.
In fact, these numbers suggest that it's impossible for there to be some hidden variable determining each photon's state with respect to each filter. In other words, it suggests that it's not even possible for these photons to have some definite answer to the three questions: would it pass through A, would it pass through B, and would it pass through C, before those measurements are actually made. What we'll do here is a proof by contradiction. Imagine one of four questions there to be
and filter block or block. C. Let's look at a particular arrangement of our three filters. A, oriented vertically, B, oriented 22.5 degrees from vertical, and C, oriented 45 degrees from vertical. We're going to compare just how many photons get blocked when B isn't there with how many get blocked when B is there. When B is not there, half of those passing through A get blocked at C.
Okay, 45 degrees is half. That makes sense.
That is, filter C makes the lamp look half as bright as it would with just filter A. But once you insert B, 85% of...
So, because the cosine of 45 is the square root of 2, or square root of 1/2. Square root, it's 1 over the square root of 2. The square root, you get 1/2. Okay. But if you put this guy in the middle, and this guy, go away the gum, then this guy, 22.5 cosine squared is 85. Let's get a calculator. Calculadora. Scientific. So 45. Where's cosine? Trigonometry. Cosine squared is 0.5. Okay. 22.5 cosine is 80. It's 0.853. Okay, it's not exactly 0.85. What's that noise? Let's see. Let's put it on quiet. Okay. So it's about 85. About 85, okay. So 22.5 cosine squared is 85. So 85% gets through. And to 45 degrees is another 22.5 degrees. Is that true? So light comes in. No one is with us, right? Nothing here. Let me give you the link. There's the link in the general chat as well. Okay. So you start with non-polarized light. Then you polarize it this way. So it's mostly this way. But there's no difference between this one and this one. So these are two parallel experiments. Then you add this one. Which, let's say, so this one is 22.5 degrees. Theoretically, 85% passed. Now another 22.5 degrees. We know it should end up being 50 degrees, 50%, because this is 50%, this is 45. 45 must be 50%. How does this work? This is weird. But this is not even, how is this quantum mechanics? This is just a paradox that should be reproducible at any scale. We should be able to reproduce this with anything. This has nothing to do with quantum mechanics. How is this quantum mechanical? This is just this is just logical. Let me see. So okay. So light is coming in unpolarized, and then it goes through. It's nothing to do with light. This has nothing to do with light. This is to do with any phenomenon that is filtered. Any phenomenon that is filtered in such a way that, let's say, this is the rule. So I have a club and I'm filtering people coming to my club. One second. Yes, señor.
What's up?
¿Cómo vai? Anyway, okay. So this has nothing to do with quantum mechanics. This is
No, it has to do with quantum mechanics.
here. I can reproduce this with humans. So let's say I
But
am
like the numbers are weird, like the y85%.
no 85%. I just calculated. That's because cosine squared of 22.5 is 85, approximately.
Wait, cosine squared of 22.5 is 85, really?
Yeah,
Well,
basically,
no, it should be 0.5.
approximately. What?
Let me check that.
Check.
I get 0.75.
Cosine of 22.5. 22.5 degrees, right? Not radians. 22.5 cosine is 0.92. Squared is 0.85. It's fine.
Wait. What? Why am I getting these numbers on my? Let me go to pipe. Like, what the hell?
Are you doing degrees or radians? What are you doing?
I'm doing degrees, but it's getting me like really. It's getting me negative numbers. Like, what the fuck?
Are you doing radians? You're not doing degrees.
No, but I put it in degrees.
Okay. 22.5.
Yeah, like I put it in degrees on Google, and it says -0. What the fuck?
Just use a normal calculator.
Yeah.
Anyway, it doesn't matter. I checked. It's fine. Anyway.
Yeah.
So let's say I have a club and I filter only people that are that have let's say when I asked them a question. I asked them, are you like, what's your polarization? So the person says, I am 0 degrees. Okay, then I let them in. If they are 90 degrees, then I don't let them in. And everything in between, I let them in based on the cosine squared of what they say. Right? It's
Okay, but the weirder part is when you put them together like this, then you get like 50%.
yeah, it's the same problem. I can reproduce this with people.
Okay.
This is not a problem of quantum mechanics. This is a problem of a paradox of logic. We have to resolve this logical paradox. Nothing to do with quantum mechanics. So let's go back to the club.
85% of people pass.
I cannot understand what you're saying. What?
So 85% of people pass on this, right?
Sure. So let's say, yeah. So let's say we have random people. They're all from 0 to 90 degrees. We have thousands and thousands of people. So a person comes in, what angle are you? He says, 0. Oh, 0, walk in. 90 degrees? No, you cannot walk. 45 degrees is 50%. 22.5 degrees is 85%. It's just cosine squared. Okay. And then let's say I have another filter.
Oh, yeah,
Again,
right. Same.
I have another filter. And again, I asked them the same question. But this filter, okay, so the first filter, wait. The first filter is 22.5 degrees. Meaning, so wait, the first filter is 0. There's 3 filters. The first filter is 0 degrees. So some people at 0, all the people at 0 come in, none at the 90 degrees come in. At the 45, half of them come in, and so on and so on. Okay.
Yeah.
Then that's the first filter. Then I have a second filter for the club. The first one is just normal entrance. The second one is VIP 1, and then there's VIP 2. So VIP 1, I set to 22.5 degrees. So 22.5 degrees, what does that mean? So if you are at 22.5 degrees, I let you in. I ask you, what are you? And you tell me I'm 22.5. 22.5, you walk in right away. What if you're 0?
Yeah, you have a 15% chance. But this is interesting because it corresponds to like it corresponds to amplitudes of the wave.
What's interesting? What you said, this is interesting. What do you mean this?
Yeah, like the quantity that passes, like why is it cosine squared? I'm thinking about that.
Because cosine squared plus sine squared equals 1. You need the probability to add up to 1. So the cosine is the people you let in, the sine is the people you don't let in. Together it has to be 1.
Yeah, that's true.
Okay, so it's fine. Okay, so start over. So the first filter I set to 0 degrees. I tell the girl at the front desk, anyone that identifies as 0 degrees, you let them in. 9 degrees, you don't let them in. 45 is 50%, and so on. Cosine, you take the cosine squared of the difference. Okay, so she lets in a bunch of people. Then there's a VIP 1. So that was filter A. Now filter B. Filter B is a different girl. I tell her, I'm setting you to 22.5 degrees. What does that mean? That means you ask the people what is their degree. If it's 22.5, you let them in. What if it's 0? Well, if it's 0, they're off by 22.5, so it's 85%. Right? 0, the guys that came in at 0 from filter A, they have 85% chance. They have 85%. This 85% is nonsense. Well, what are they talking about? This 85% is not the filter from A to B. It's from 0 degrees to B. People who are at 0 degrees are 25% off. They walk in at 85%. This is completely wrong. Right?
More or less. I still have some doubts about why the cosine squared. But we can continue.
Okay. So, I mean, okay. But look at this. This is weird. The people, what do you mean 85% pass? That cannot be right. That cannot be right, because it's the 0%, it's the 0 degrees. The guys that came in at filter A, all the 0 degrees walked in, right? All the 0 degrees walked in, right?
Yes.
Yes. But some of the 45 degrees, half of the 45 degrees also walked in, right? Some people at 22.5. 85% of those that were 22.5 degrees walked in. You're not following, are you?
Yeah, I'm following. But
okay, so what they say 85%, that's obviously wrong. That's true for the 0 degrees. The 0 degrees, they're 85%.
Wait, the 0 degrees are 85%?
Of course, 0 degrees filtered by B.
Oh, okay.
0 degrees filter at 22.5. They're off by 22.5. They walk in at 85%. And the same for 45 degrees. The people that were initially at 45 degrees, that's half of the initial, between A and B, half of the 45 degrees made it in, passed. When it comes to going through B, it's half again. I mean, this 85% is complete nonsense.
Okay.
85% is the 0 degrees. He's just referring to the 0 degrees. This is not true. The 0 degrees, that's all those that were 0 degrees, they passed. But there's other people between 0 and 90 degrees that also passed. And we're not talking about them at all. Let's see what he says. This makes no sense. So there's 3 filters.
A, oriented vertically, B, oriented 22.5 degrees from vertical, and C, oriented 45 degrees from vertical. We're going to compare just how many photons get blocked when B isn't there with how many get blocked when B is there. When B is not there, half of those passing through A get blocked at C.
Let's see if this is true. I mean, he's saying half of these get blocked by this. We'll soon see if that's true. I don't even know if that's true. I don't know if that's true. So let's start with this with A. So A says if you are at 0, you pass. If you're at 90, you don't pass. If you're at 45, half of you pass. If you are at 22, if you're at 22.5, 85% pass. Am I getting this right? Is this correct? So the people that came through, it's a mix. The people here are between 0 and 90 degrees. A lot of them are 0. Very few are at 90. Or no one is at 90. No one is at 90. At 0, there's a lot. Maybe there is a linear relationship from 0 to 90. Is it a linear or is it cosine squared? It's cosine squared. So let's draw cosine squared. What does it look like, cosine squared? It's got nothing to do with what he's talking about. Nothing to do with what he's talking about. He's not.
Oh, yeah, the square is the magnitude. That's true.
Wait, let's draw it. Either I'm losing my mind or I'm losing my mind. What he's talking about has nothing to do with reality. Okay, let's make a new one. Could it be so simple that they got this wrong so simply? Okay, what do we want to look at? This is polarization. Do you think we're going to figure it out?
Yeah, probably.
Yeah, I agree. I mean, we've done so well so far, so I don't see. I was just listening, when I'm not, like, I started watching. I'll show you what I'm watching. See, I'm watching this girl. Kathy loves physics and history. So she's unbelievable. She has very short episodes, and she goes through everything from the foundation of science, basically.
That's good.
This is also good. This video, it's in German, but it's good. And this is good stuff. This is good stuff. This is Feynman.
Other things.
Richard Wolff, I don't care. Casimir, yeah, I was studying the Casimir effect. Yeah, this is unbelievable. Ohm's law. He was rejected. He lived his life basically mostly rejected. Yeah.
Why? This was so simple.
Because his law contradicted somebody else who was very big and destroyed his career. Yeah. I mean, just destroyed his life.
I had no idea.
Yeah. And Planck basically promoted Einstein. Planck was like this promoter. He had this vision that he needs to promote young, up and coming. He was very nice to everyone else.
Interesting.
Yeah.
Maybe he preferred other Jewish scientists.
No, he wasn't Jewish.
No, he was Jewish. I thought he was Jewish. I thought
Planck?
I always think
no, I don't think Planck stayed in Germany. Planck was like pro-Nazi.
He was German. Okay.
And Maxwell's the Quaternions from Hamilton. She has a chapter about Hamilton.
That's interesting.
It's unbelievable. This is the invention of
video. Give me that.
This is the invention of vectors.
Yeah, but quaternions were more complete actually.
I don't know.
Yeah, they were.
I don't know. I don't have an opinion. I like vectors. Vectors won because they were so simple. Vectors are
Yeah,
so
vectors are
simple.
the vectors are.
Oh, this is Hamilton. You want this one more. Hamilton basically destroyed his life because he promoted the quaternions, and no one really they never caught on. So he wasted his life promoting the quaternions. You see, I never heard of these words until today. Maxwell is amazing. Maxwell is unbelievable. This gave me so much insight about the speed of
Oh, I want to see that because I want to see like the original Maxwell's equations with the quaternions.
yeah.
I've seen
This
I've
is
seen them once, but I don't remember them very well.
so Maxwell in the beginning he had to decide who is he gonna pick up from. So he decided to pick up from Faraday. Now Faraday didn't know any math. So Maxwell read Faraday's work on electricity, on electric field. So Faraday invented electric fields with no math, and Maxwell invented field vector fields without Gauss's law. He basically invented Gauss's theorem without Gauss's theorem.
Yeah, we did.
Unbelievable. Just you, but this gave me so much insight because until today I was stuck in the dialect. I had a video that the speed of electric field is instantaneous. That's what they say. And today I was listening to Maxwell how he developed Faraday's law, which is using Gauss's law, and it's clear that it should be restricted by the speed of light. Can't believe until today I was trapped in dialect misunderstanding, misconception.
What was his misconception? That
Dialect. They believe that the speed of propagation of the electric field is infinite.
is instant. Do you
Instant.
believe that?
They believe it. We saw the video.
Are you
I
sure?
think yeah, definitely.
I'm
They
not sure.
believe in Lorentz contraction, electric contraction.
Yeah, but that doesn't mean it's instant.
Yeah. That's exactly what it means. It's
No, it
yeah.
does.
I think it does. It doesn't matter. Look,
What,
we
it's not
we can
instant.
go back. We can go back and watch
No,
it.
it's no point. No point. You're still watching Hillary Clinton in Benghazi.
Who am I watching?
That was a misclick.
Misclick? Where? Benghazi?
Hillary Clinton
Where?
in Benghazi. Down.
No, I did not want. I don't know how this popped up. Misclick. No, it's watched later. I don't
Oh,
know how. It's probably from 1,000 years ago. No, I don't care about this anymore. I know why she did what she did, and she had good intentions.
I don't think she had good intentions, but okay.
No, they have good intentions. Politicians have usually good intentions.
Really, you believe that?
Yeah, but they destroy the universe with good intentions. Good intentions is not. It's useless.
I don't know about the good intentions of politicians. I don't think so.
Anyway,
Okay.
I think Eric is an idiot, and so is this guy on the left. What's his name? Keeping is an idiot. I think she's an idiot.
You think so? You think
Small,
everyone is idiot? And you say you're the best?
Smolin. I wouldn't say Smolin. Look, she's a terrible person.
Why?
They're each
I don't know.
She believes in global warming.
Oh,
Like
come on.
she's a
You
real
could not
no no
say.
no no no. She really believes, like she is crazy about global warming. I mean, she's a Looney Tune. When it comes to global warming, she's completely out of her mind.
I don't know. I mean,
Um,
she does criticize climate scientists very often. I think she has a reasonable position.
no, completely not reasonable. This is Maxwell equations, good stuff.
I think she's like,
Hamilton.
she believes warming, but she's not alarmist.
She is an alarmist, an
No,
extremist. Yeah, yeah, extremist alarm. These videos are repeating. It's showing me the same videos, exactly
yeah,
the
yeah.
same.
Sometimes it does that.
Now, this guy, you're not going to believe it. Fermion Physics, he's a high school student and he teaches super duper advanced stuff like you cannot believe. He's like in like a year ago he has, oh, today I graduated high school, I'm going to go study physics. Meanwhile, his videos are like you cannot believe the level. You just cannot believe the level. He teaches the most advanced stuff like it's nothing.
I mean, he's already made the course.
Yeah. So here is his
You
Hawking.
won't.
He teaches why everyone is wrong about Hawking radiation.
Really? Already
Yeah,
doing that?
Rutherford scattering. I don't know why it's not playing. How to derive Newtonian gravity. That's the only lecture that he gave that I actually could follow. Quantum field theory, very advanced. Casimir effect. You see, he's a high school kid. He's
Yeah.
a high school. He's a black high school kid. Genius, like the biggest genius I've seen in my entire life.
Casimir effect. Yeah, Casimir effect. What does he say the Casimir effect is, by the way?
Casimir is when you put two plates.
Yeah, I know, but what causes that? That's the question.
So
I think it's a
it's
charge effect.
it's a what?
A charge effect. A charge effect.
No, they ground both plates, so it cannot be charged.
No,
And
it
it's
can
weight
be. Can be Van der Waals effect. It can still be that. You can
Undervolt.
polarize neutral.
No,
Yeah, you can polarize neutral things.
look,
So,
they.
yeah.
I don't know. I don't know. They say that they tested it, and that's the result they're getting. You could say it's gravity, but they use very lightweight plates. Look, they measure it. They rule out everything, and they measure it, and it's as expected. They actually made a prediction as to
Yeah, the
what the
prediction
force
was
should.
based on what?
But I don't know, but as far as I know, Casimir made the prediction, and then somebody else tested it, and the prediction was correct.
Mm.
Um, yeah, this is just Casimir, nothing but Casimir. I I was just trying to figure out the mass of the ether. Um, yeah, this is nothing but Casimir. Quantum fields, Bell's inequality. This chick is hot.
Mm.
This guy, this guy's useless. Absolutely
You don't like
useless.
that guy.
A strong force equals the Casimir effect. No, no, that's ridiculous. That he's ridiculous. He's a joke. Design and measurement of Casimir forces. What else? Einstein. The origin of mass. So there's a video, the last video I watched as I was taking the dinner break was this guy.
Albert Einstein was awarded the 1921 Nobel Prize in Physics for the photoelectric effect. But why? At the time, just like now, Einstein was far more famous for his work on relativity. Well, it all has to do with a man named Philip Leonard, whose experiments in the photoelectric effect inspired Einstein's theories. Leonard is a fascinating person who first inspired and befriended Einstein, and then, due to an odd combination of his love of physics, scientific disappointments, nationalism, and mental weakness, became one of Einstein's greatest nemesis. This is a physics story and
prepare to laugh.
A story of a man's descent into madness and fact.
You're gonna laugh. It's really funny. I mean, funny, sad funny.
So buckle up and let's go.
Electricity, 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 electricity.
A young German scientist named Heinrich Hertz discovered the photoelectric effect in May of 1887. See, Hertz had just discovered radio waves by adding an antenna to an induction coil, so that large sparks in one end of the room could be caught by making little sparks in a receiving coil a distance away. Because the spark in the receiving coil was really small, Hertz decided to put it in a dark box, so that the light from the bright spark from the induction coil wouldn't distract it. To his surprise, when he did this, the spark in the receiver became, quote, decidedly smaller. Hertz started to put all sorts of screens between his transmitting spark and his receiving spark, and found that glass would reduce the spark, but quartz did not. As glass blocks ultraviolet light and quartz does not, Hertz decided that the energy from the ultraviolet light must be amplifying the electric spark. Aside from that one observation, Hertz didn't attempt, quote, any theory respecting the manner in which the observed phenomenon are brought about. This was eventually called the photoelectric effect. Photo for light, electric for, well, electric. Although Hertz didn't come up with any theories, many other people tried, including a 27-year-old Hungarian grad student of German descent named Philip Leonard, who was struggling to get a permanent position. At the time in Germany, 27 was considered quite old not to have a permanent position in physics. I know. Anyway, Leonard observed that when smooth metal plates were hit with strong ultraviolet light, they started looking a little less smooth. Leonard had this interesting theory that the electricity could only be carried by dust, not by gases, and that the UV light was freeing the dust, which caused the plates to look rough. This theory was roundly ignored by basically everyone and seemed to go nowhere. However, 3 years later, Leonard's luck changed as he managed to get a job as an assistant to his hero, Heinrich Hertz.
That's very interesting. So it cleans the plates. It removes the dust. It sounds like the electrons leaving are carrying dust with them.
Hertz was studying cathode rays, or invisible rays that are made in a vacuum and can make phosphorus glow. Hertz found that cathode rays could travel through thin pieces of metal, and he told Leonard to make a vacuum tube with an aluminum barrier. You might ask why Hertz didn't do the experiment himself. It was probably because Hertz was starting to get terrible headaches and feel sick all of the time. Left alone in the laboratory, Leonard not only studied cathode rays with an aluminum barrier between different vacuums, he took it a step further and made an aluminum window between the vacuum tube and the air, and found to his surprise, the cathode rays could travel a few inches in air. Leonard was sure that his Leonard tube would finally make his name in science, and he published his results in December of 1893. Tragically, Hertz died mere weeks later, and Leonard took time off his research to edit German and English memorials of Hertz's work and biographies. This was an unfortunate timing for distraction for Leonard, as just the next year, another German scientist named Wilhelm Röntgen was experimenting with a Leonard tube with a heavier phosphorescent screen and discovered a new ray, which Röntgen called X-ray. Suddenly, the whole world was in an X-ray craze. At first, Leonard was excited by this.
So what was the difference between the Leonard tube and the Röntgen tube? Sounds like it's the same. Sounds like Leonard discovered Röntgen, like X-rays. I don't know.
And wrote Röntgen.
So why didn't he notice that I don't know.
A nice letter, quote, because your remarkable discovery caused such remarkable attention.
Could have killed him.
In the farthest circles, my modest work has also come into the limelight. And at first, Leonard was correct, as they both started receiving numerous medals, including the Rumford Medal in England and the Matteucci Medal in Italy. Leonard finally got an associate professor position, and after setting up his laboratory, decided to get married. As he put it, quote, there was an abundance of daughters of professors who were waiting to be married. Soon he was made a full professor, and his career and family life seemed secure. However, in 1897, an Englishman named J.J. Thomson proved that the cathode ray wasn't a type of light at all, but was instead a beam of charged particles that we now call electrons. With the discovery of the electron, Leonard...
Wait a minute. So Röntgen is not electrons. So when is it electrons and when is it not? When is it X-rays and when is it electrons?
I mean, there will be X-rays.
No, so Röntgen is there's no potential differential. If you have a potential differential, then it becomes electrons. Okay.
Found that all of his work on the cathode ray was made moot. Even worse, if the cathode ray was a particle and the X-ray was a beam of ultraviolet light, which is what we now think, then Leonard's discovery that cathode rays could travel in air had very little to do with Röntgen's discovery of X-ray. In other words,
Leonard was given awards for X-rays, but his was not X-rays. His was an electron beam. He discovered an electron beam. He was getting recognized for the wrong discovery. So Leonard discovered the electron beam and was getting awarded for the X-ray.
Thought that Röntgen had just discovered a new type of cathode ray in air, but really, Röntgen had discovered something new, and Leonard hadn't. It was a crushing defeat. Leonard repeated.
Oh, so it wasn't even a discovery. Oh my God.
He did J.J. Thomson's experiments and found that, yeah, quote, in every respect, the rays behave like moving masses carrying negative charge. Then Leonard had an ingenious idea. What if his old theory, the charges were only carried by dust, was right if the dust was really just electrons or cathode rays? In October of 1899, Leonard published The Generation of Cathode Rays with Ultraviolet Light, where he demonstrated that ultraviolet light produced electrons by shining ultraviolet light through a quartz screen into a vacuum tube and studying.
Okay. But that's not the point. I mean, these are good videos to go through because these are actual experiments.
The photoelectric ray inside the tube. Unfortunately for Leonard, J.J. Thomson published similar results at about the same time, so he felt like he didn't get the acknowledgement for that discovery. Then, what should have been a breakthrough to understanding the photoelectric effect happened in December of 1900. That is when a German scientist named Max Planck published his equations for blackbody radiation, where he assumed that light came in little energy elements.
So his equation is E equals h mu. Okay.
Yeah.
H nu.
With energy equal to a constant times the frequency of light. This would explain why ultraviolet light could have the energy to produce the photoelectric effect, but visible light did not, as ultraviolet light has higher frequency and therefore is composed of elements of higher energy. However, Leonard didn't see the connection, and frankly, neither did Planck. Meanwhile, in 1901, the Nobel decided to give the very first prize in physics to Röntgen for discovering the X-ray without mentioning Leonard at all. Leonard was very upset and pushed
At this point, they realized he had nothing to do with it.
everywhere that he was unfairly treated. Determined to make his mark some other way, Leonard continued to study the particles created by ultraviolet light in a vacuum tube. Leonard found that if he added a voltage the wrong way, he could drive the electrons back to the irradiated plate, quote, in the same way as a stone thrown upward falls back to the ground. Now he could experimentally add just enough voltage to drive back the electrons, and therefore measure the maximum energy of the electron, which is obviously related to the speed of the electron.
So he discovered the photoelectric effect. So it was completely his.
To his surprise, the initial velocities are independent of the intensity of the light. In other words, more intense light created more electrons, but it didn't give the individual electrons more energy. What did this mean? Well, Leonard had an interesting, but it turned out wrong conclusion. Leonard thought that since the speed of the electrons was independent of the intensity of light, that the energy didn't come from the light at all. Instead, he thought the light released energy inherent in the molecule, like, quote, the fuse in firing a loaded gun. This triggering theory was generally accepted as true, and even as late as 1909 was written as one of the generally accepted laws of physics. Then in 1905, three events drastically changed Leonard's life. The first was that Leonard was awarded the Nobel Prize in Physics for his work in cathode rays. This despite the fact that 14 top scientists nominated J.J. Thomson for discovering the electron, and only 2 scientists nominated Leonard. Don't worry, Thomson won it the next year. In his speech accepting the award, Leonard freely acknowledged the work of others, including many Jewish scientists, and admitted that he wasn't always the person who brought ideas to fruition, saying, quote, I have by no means always numbered among those who plucked the fruit, but I've repeatedly been only one of those who planted or cared for the trees. The second event was in June of 1905. A patent clerk published a paper where he proposed looking at many phenomena, including the photoelectric effect, if light came in little energy packets. This view of light led to a photoelectric effect equation, which worked with Leonard's results, but were not proven by them. The third event was in that same miracle year. Einstein published a paper on special relativity. At first, Einstein and his ideas didn't offend Leonard. In fact, Leonard, or possibly an assistant, saw how often Einstein referred to Leonard's work and sent him a copy of his latest paper. Einstein replied with an enthusiastic letter in return. It took Leonard 4 years to reply to Einstein, but when he did, he was effusive with his praise, especially considering that Leonard was a Nobel Prize-winning physicist, and Einstein was virtually unknown. Leonard gushed, quote, what could be more exciting for me than when a profound, comprehensive thinker like you finds favor with some points from my work? Around this time, 1909, Einstein learned that a friend of his, Jacob Laub, had gotten a position as an assistant to Leonard. Einstein wrote Laub, quote, I think the opportunity to work with Leonard is worth far more than the assistantship and income combined. Leonard is a great master and an inventive thinker. However, Laub's relationship with Leonard quickly soured, and Einstein's went with it. See, Leonard was a big believer in something called the ether, an invisible, weightless material.
Unbelievable. So Leonard had it right. Einstein got it wrong. But look at what happens next.
Yeah, what was the theory of Leonard for the photoelectric effect?
No, it was ether. Leonard believed in the ether. Here,
no, but what was his theory for the photoelectric effect?
He didn't have a theory. He just that it's just an ignition theory, that it just unlocks the electron, and the speed of the electron is the natural speed of the electron. Nothing to do with the photons.
Oh, okay.
I think Einstein would come and say that no, it's the kick comes from the photon or something, I'm assuming.
And Einstein's went with it. See, Leonard was a big believer in something called the ether, an invisible, weightless material that fills the entire universe.
She said weightless. Why is she saying it's weightless? How could anything be weightless? Invisible? Okay.
Einstein's went with it. See, Leonard was a big believer in something called the ether, an invisible, weightless material that fills the entire universe, even in a vacuum, so that light will have something to vibrate. After all, they thought, if you have a wave, you need to have a wave in something. In fact, Leonard insisted that electrons were really just pieces of ether. However, by
So he insisted electrons were pieces of ether. That's genius. So he knew electrons were waves. His intuition, pieces. So maybe he did not have the intuition of the wave, but he
knew they behaved like waves. He had to know. Like he was building a beam.
No, they didn't have. No, they didn't. Only de Broglie came up with the notion that electrons are waves.
No, de Broglie is kind of weird stuff already.
No, No, everything I'm doing is based on de Broglie. My
No,
entire
I think he
notion.
probably had the notion that the electrons were waving. I think he
What?
did. I think he did have the notion that the electrons were waving.
Not very likely.
I
It
think
was revolutionary when de Broglie wrote in his PhD.
yeah, but the
But
Broglie is different. It's already quantum mechanics. It's not the same.
Okay. Look, she says that he believed that electrons were pieces of ether, not waves in the ether.
Yeah, but they
This
could
magical
wave
material
in the ether.
But
Right?
we need to see. We need
Like
to see what
piece of
he.
water can wave in the water.
That doesn't make any sense.
was losing ground because of Einstein and relativity, as the odd effects attributed to the ether could just be because of the limitations of the speed of light. Lobb complained to Einstein
Let's see.
in something. In fact, Leonard insisted that electrons were really just pieces of ether. However, by 1910, this magical material was losing ground because of Einstein and relativity, as the odd effects attributed to the ether could just be because of the limitations of the speed of light. Lobb complained to Einstein
Such nonsense.
Yeah.
that Leonard was wasting his time on useless experiments. Einstein wrote back,
So these idiots were complaining that he was wasting their time researching the ether. Meanwhile, these two were the idiots, and Leonard was the genius.
quote, Leonard's recent lecture on these fanciful ethers appears to me almost infantile. Further, the study he commanded of you borders on the absurd.
I mean, Einstein himself in 1920 agreed that the gravity is the ether. So
I'm sorry you must spend your time on such stupidity.
I wonder if he ever told, like, this is just about 10 years later. So did he ask Leonard for, like, did he say he's sorry for objecting to the ether? Probably not.
Einstein tried to get Laub a new position, which earned Leonard's ire for both men. Leonard started treating Laub very cruelly, and when Einstein heard of it, he wrote Laub, quote, Leonard is really a twisted fellow, so entirely composed of gull and intrigue. However, you're considerably better off than him. You can get away from him. However, he must do business with this monster until he bites the dust.
I mean, maybe he was an asshole. I don't know, but it sounds like he had the correct direction.
Then, in 1914, an American named Robert Millikan published his work on the photoelectric effect, that he had started to disprove Einstein, but had shockingly confirmed every detail of Einstein's photoelectric equation. The triggering theory was completely destroyed.
The triggering theory is that the speed of the electron is innate. It's not from the photons.
addition, that same year,
That's Leonard's theory.
was the beginning of World War I, which Leonard was a vocal German supporter. In fact, Leonard signed the Manifesto to the Civilized World, which included the line, without German militarism, German civilization would be wiped off the face of the earth. Not only did Einstein refuse to sign the manifesto, he co-wrote a rebuttal. When Germany lost the war, Leonard was devastated. And to make matters worse, that very same year, an English astronomer used a solar eclipse to prove that gravity could bend light. In other words, he experimentally proved relativity. Einstein became the most famous physicist in the world, and most scientists believed in relativity. Jealous and heartbroken, Leonard decided
Relativity has nothing to do with the theory of gravity. Relativity is nonsensical, and the theory of gravity is fine.
that it was all because Einstein was Jewish, and it was a big Jewish conspiracy to get rid of ether, push relativity, quantize the photoelectric effect, destroy Germany, and discredit him. Leonard made it his life work to remove Jewish science from Germany. He tried to keep all positions for pure Germans, and he also used his influence with the Nobel Committee as a previous winner to try to keep Einstein from joining their ranks. In 1919, Leonard managed to get his friend and fellow anti-Semite Johannes Stark a Nobel Prize, despite the fact that Leonard was his one and only nominator that year. By 1920, Leonard was heading the
How
anti-Einstein
does
and
this Nobel
anti-relativity.
Prize thing work? Like, there's a
What?
guy who has one nomination and wins.
Well, I don't know. I don't know. It's a club, you know.
Groups with speeches, debates, and anti-Semitic publications. The 1921 Nobel Committee became so confused by the pro and anti-relativity factions, they didn't give anyone a Nobel Prize that year. The next year, a young Swedish scientist named Carl Osin found a way around the whole mess and suggested that Einstein should win the Nobel Prize for the previous year, quote, especially for his discovery of the law of the photoelectric effect. Then Leonard went completely off the rails. By 1924, Leonard was a devoted fascist, and he and Stark published an article in the newspaper saying, quote, Hitler and his comrades appear to us as God's gift from the times of old when races were purer. By the 1930s, Leonard started publishing books of science separated by their races, which became the backbone of Nazi science.
Okay, whatever. Yeah. Everybody was confused. Everybody was confused back
Everyone
then.
is an idiot. That's what you should say.
Yeah,
All
okay,
idiot.
Okay, let's try and figure this thing out. Okay, so this makes no sense. I don't know whether, I mean, how could, I mean, these are
I mean,
these
the
are
85%
mathematicians.
is just the magnitude. So
What?
The 85% is just the magnitude of the component.
Wait, okay, look at this. So from here to here, over the A filter, what is the percent? What is this percent? right? They don't tell me what this percent is. Why are they telling me this
Depends
percent?
on the previous one.
I mean, assuming it's everything between 0 and 90, it's linear. So what gets through A?
Yeah, it's 50%.
What? Why?
50%.
Why?
Why
It's
not?
100%. No, it's 100%. It could be 50%. It's 100% of the 0. It's 0% of the 90. It's 50% of the 45. Yeah, you're right. It sounds like it should be from symmetric argumentation. It's 50%. So this is 50%. Okay.
Wait.
Then from here to here, why is this 45 degrees? Why is this 50%? Let's see.
Is it 50%? Because
This is 50% because of symmetric considerations.
yeah, it has to be.
Yeah, it has to be. However, so here it's lopsided towards the 0 degrees. 0 degrees, there's a lot of 0 degrees here. There's no 90 degrees. But is it linear between the 0 and the 90? Yeah, I think it's linear. So I was about to look at this. So at 0 degrees, this is the graph for 0 degrees. This is the filter, 0 degrees, the direction of the filter, 0 degrees. Okay, incoming light. So light coming in, so this is the degree of the light coming in, of the incoming light. The incoming light, if it's 0 degrees, then it's 100%. That's 0 degrees. If it's 90 degrees, then it's 0. And it looks like it's linear.
It's
right?
not
So
linear.
it has to be. At 45 degrees,
No,
it's 50.
not.
It's not linear?
No, it's like
not?
circular. It's like
But it has to be. At 45, it has to be 50. Wait, this is percent.
yeah.
This is
it's degrees.
this is 50%, and this is 45. At 45, it must be 50%. Sounds like it has to be linear. What else could it be?
But it's not linear. It's like it's a weird function.
You're saying it's the cosine squared, but how could it be at 45 degrees? How could it give you 50%?
It can. I don't know how the cosine squared would look like.
Let's go. Let's draw a graph. Let's go to graph. So this is cosine squared of x.
Wait, no.
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 X.
Okay,
that's okay. Let's look at cosine.
No, this is fine. This is fine.
Okay. So
we can see it already.
But this is not. This is radians, probably not degrees.
It doesn't matter.
You're saying
we can see it already. Like, look.
Oh, that's why it's 50% because it has two inflection points.
Yeah.
So it ends up being at 45 degrees. It's 0.5. I'm assuming this is.
Yeah, this is 45 degrees. That's 45 degrees.
Can we tell it x degrees?
What? It works?
I don't know.
It did, sort of.
No, that's not degrees. It has to be. Let's see.
Well, it looks like it is degrees. Wait.
No, this is wrong. What's wrong? Use
Like,
parentheses around the argument of. Oh, this is wrong.
oh yeah.
Okay. So the green.
Degrees? No, it can't be degrees.
No, it cannot be
I don't know
degrees.
what tag is there.
Deg is maybe something else.
Yeah. What?
Instead of x, maybe just say degrees.
What the hell? Is that some variable?
I don't know. Can we tell it I want it in degrees? What's going on? Let's remove some stuff.
Yeah, go to like the options.
Add slider options.
Yeah, that's like that. Is exactly what? What's that? Nothing special. Just put X there.
It doesn't make. What is 1?
Like 1 radian.
Oh, it's in radians. That's terrible. So
And
we could just say pi. Oh, let's just say.
It
So
works.
I think
We know more or less what's pi over 4.
pi, isn't it pi radians or x over pi radians?
What? I don't know. X over pi?
5.
Oh, I get on 5.
Maybe over 2 pi? Maybe over 2 pi? No. Is it?
No,
Maybe 360? Isn't it? Maybe, I don't know.
No, it's fine with the radians. We can still read it. Like we know that pi over 4 is about 0.8. Just do X. Just do X.
You saw the problem with x, I mean. Or we can do it with radians.
Doesn't matter. No, I don't know what those degrees are. Sine rad.
RAD. No, when you do R, it just does 3 equations.
Oh, it does R, A, and D. Yeah, I see.
R times A times D.
Yeah.
This is D, E, G.
Okay, that's fine. We can.
Yeah, it's fine. Yeah.
Just zoom in. Just zoom in and we can see it.
Okay. All right, so we just need a shape. So this makes, if this is 1.5, so this is about 0.75. It's fine.
Yeah.
Okay, so that's the shape. So where, okay, so let's get back to here.
But that's not really 45 degrees. Just go back.
1 second.
Yeah, wait. I'm seeing the video. Have you gone back?
Go back?
Yeah, go back. No, go back to the chart.
The graph?
Yeah.
Okay.
Okay, so where's 45 degrees?
This is 45 degrees.
No, that's not 45 degrees.
No, it's not 45. That's yeah.
5 degrees.
Yeah, it's 45.
No, it's not.
Yeah.
No, that's not 45 degrees.
Yeah, because This is cosine. So cosine is 0. So this is 90 degrees.
So
let's just do x over 2.
that didn't help very much.
X times 2x. So this is 2x.
Okay.
So this is the 45 degrees. Yeah, it's 50%.
Oh, wait. Oh, okay. I was seeing that wrong. Yeah, okay. Fine. Yeah.
Okay. So 45 degrees is 50%. Okay. 22 is half of that. Let's do.
Or
Yeah. You want to go to sleep?
yeah, soon.
Okay. Cosine E4x. Okay. Cosine 4. So this should be 22 degrees, 22.5. 22.5, who knows? Oh, there it is. Yeah,
Yeah.
0.8, it's approximately 0.85.
Yeah, makes sense.
Fine, but that's not correct. That has nothing to do with what we're looking at. Nothing to
We're
do
going
with
to
this.
compare just how many photons get blocked when B
Because you need to integrate to know.
isn't there with how many get blocked when B
Let's watch and I'll tell you.
is there. When B is not there, half of
Okay, let's talk about A. A, you need to integrate. You need the area under the curve to discover A. So the area under the curve of cosine squared is A. Which is A? Too many lines.
I don't know why the red one is not appearing.
Okay, it's this one. It's this one. Okay. So you need the area under the curve. You need the integral. How do you do integral?
I don't know.
Oh, there it is.
There, I don't know.
Integral.
That's okay.
You just say integral from 0
Pi over 2.
pi over 2.
Yeah.
What's the issue? Integrand must end with like dx. Okay, dx.
Oh, right.
So the answer is 0.78.
But the answer to what?
The integral, it's 0.78 of 100%. It's about 79%. 70, but it's meaningless to even discuss it. It's meaningless. This entire discussion is completely. Wait, I'm not sharing it. This entire discussion is meaningless. This is completely bonkers. This has nothing to do with reality. If I understand polarization, if after our discussion and listening to them, if I understand polarization, then this makes no sense. Because you need to integrate, but I don't even care about the integration because I need to preserve. I need to look at the graph itself of the cosine squared. The probability distribution of the polarized light in here is cosine squared.
No, the cosine square is just the magnitude. Just gives you the magnitude of the.
No. It's the cosine squared. It's not just the magnitude. It's the magnitude for each degree. Each degree. Let me just get the cosine squared x. Okay, let me remove the rest of the lines. We don't need any of them. Okay. So for 0 degrees, they all come in. For 90 degrees, none of them come in. For 45 degrees, 55%. For each degree, you need this graph. This graph describes exactly. You have to preserve this graph. This graph is the input for C. You cannot just say C 45 degrees is some number.
Of those passing through A
No,
get blocked at C.
no. You cannot say that. You absolutely cannot say that. Because there is a distribution. The distribution here is cosine squared x. And this 45 degrees applies to this distribution, so that if you want to talk about the 45 degrees, okay, so talk about the 45 degrees. So the 45 degrees, so all of these will be passed in. All of these, right? All of the 45 degrees, right? Right? Because of the guys here, 50% let's call this pre-A. So pre-A, some of them were at 45 degrees. 50% of them are here. All of the 45 degrees that are here, which is 50% of the 45 degrees that were here, will pass. When he says 50%, he's talking about the 0 degrees. That's just a sliver. He's just talking about this. The guys that were initially at 0 degrees, which is 100% of the original, these guys now, only 50% of them will pass to the next stage. This is completely irrelevant. It has nothing to do with the discussion. This is nothing to do with quantum physics. This is just misunderstanding. I don't even want to say probability. This is just misunderstanding. This is just a misunderstanding of the problem. It's nothing to do with anything. It's not even physics. It's just misunderstanding the problem. Wait, somebody's with us. Yes, Andrew. What do you want?
What's up?
Are you listening? Andrew, can you hear me? Okay, he's muted. So I don't think he's listening. Anyone listening right now just got their shoes blown off. Wait, what does he want? I do. You do what? What do you want, Andrew? What do you want? Stop doing nonsense. You can join the discussion. Stop with the nonsense. Anyway, okay, Andrew, stop. Okay. So, unless I don't understand anything that's going on. So this guy says there is an 85% chance you will not understand this video if you watch it once. No, you cannot understand because it's wrong. I heard they are patching this in Universe version 2. I saw this video when it first came out. Okay, let's see if anybody else caught on to this. Oh my God, Andrew, stop. So let's see, this is at 4:42. Let's see if anyone talks about... No one makes actual comments. They're all saying nonsense. Nobody caught on. 205 photons are waves. Look, you correct me if I'm wrong. Did we misunderstand polarization?
I'm thinking about it still.
Maybe we misunderstood polarization. I don't know. So how do we know the photons are not being twisted when passing through a filter? I'm not even asking that question. That's a good question. I'm not even asking that. I'm curious if the authors, no one got, okay, thank God, this passed completely over my head. Yeah, this video is designed to go over everyone's head. This is not a slow video designed to explain. This is nonsense. So let's forget about this video. Let's just write a comment.
No, we could watch the rest.
How? This has nothing to do with anything. This is nonsense. How could they make... Look, either we don't... Anyway, Bell's theorem has nothing to do with polarized light. There's no entanglement here. I don't understand. This is too complicated.
Yeah, I don't think it has anything to do with that. But
so I'll just make a comment at 442. So what do we want to say? This is completely wrong unless I did not understand polarization as it was explained in the beginning. That's not how you spell beginning? Double N? So what is wrong? So filter A should give us a distribution of cosine squared x. Of this distribution is then fed into filter C. The result is not 50%. I mean, 50% of the 0 degrees pass filter C. But what about the rest of distribution that passed filter A? We must... Is it even an integral? It doesn't even... I don't even know how to begin talking about this. Like, what is it? What do you mean 50% of... Oh, no. So what they... Okay. So what they're saying is, don't forget, whatever distribution you're getting here, they're all of a single degree. They're all at 0 degrees. There's no distribution of angle here. Are you there? Oh,
Yeah, I'm here. I'm
here.
here.
Yeah.
I'm thinking.
So everything here is at 0 degrees. There is a distribution, but it's all 0 degrees. The question is, how many, who passed over? And this they're saying it doesn't matter because the input, the guys that came in, whatever number is here is in the same number here. That's why they don't care. They don't care whatever the number is here.
I think I
Amnesia.
figured this out. No, actually, I think I figured this out.
You what?
I think I figured this out.
Oh, okay. Amnesiac, how are you?
Amazing.
What's up? Are you listening to the video?
No.
No. I didn't put a link to the video. Let me put a link to the video. So what do you want to talk about?
Kind of just, I don't know.
You don't know?
Are you doing any kind of physics explanation or something?
Yeah, we're doing physics. We're doing quantum mechanics. We're trying to save the universe from quantum mechanics. Why? What do you want to talk about? Okay, let me know if you want to talk about something. Well, I'm gonna go get back to
I
killing
don't know how to
my.
draw.
You don't know how to draw? Let me check.
I don't know how to draw a pussy.
That's fine. You did a good
That's the
job.
best I could come up with.
It's very nice. It's beautiful. It's absolutely beautiful.
Oh, there you go.
Excellent. Absolutely excellent. Outstanding. Okay, let's get back to serving the universe. Okay. So some inputs, I mean, so they say we don't care who passed through A. Whatever the number is, 50%. So these are all 0 degrees. So at 45 degrees, obviously it's 50%. That's fine. So we agree with that. Okay. So everything is resolved.
That is, filter C makes the lamp look half as bright as it would with just filter A. But once you insert B,
So what he's saying is filter C takes the output of filter A, and it's definitely 50%. So it makes the output of A, it makes it 50%. It makes it 50%. That's fine.
85% of those passing.
Now here is the issue. It's because but what about the nightclub? This has to fit the nightclub. So in the nightclub, there's people of all kinds. But when they walk in, I reassign them all to be 0. When they walk in, I tell them all, okay, now you're 0. So that's fine. So whoever they are, when they walk in, I tell them, okay, now you're 0. Whatever the distribution is, whatever the number of people is, I tell them now you're 0. Okay. So of all these guys that are all 0, and now I'm sending it to 22.5 degrees, so 85% pass. And now these guys are at 22.5. I tell them all, okay, now you're at 22.5 degrees. And now I put a filter at 45. Who's making noise? Is that Amnesiac making noise, or is that you?
I don't know. Maybe it's me.
So yeah, maybe you should mute. Try muting. Let's see if it helps.
Okay, I'll mute.
It doesn't help. Okay, Amnesiac, it's you making noise. Amnesiac, you're making noise. Amnesiac, I'm going to mute you, okay? You're making noise. Okay. Let's continue. Okay, so I tell the people in the club, the guys that managed to get filtered in, I tell each one, okay, now you're 0 degrees. Then I filter them by 22.5. 85% go to VIP 1. I tell them you're each now at 22.5. You are each assigned to be 22.5. Somebody asks you, you're 22.5. That's impossible. No, it's true. It's true. These guys are 22.5 degrees. Wait, these guys are at 22.5 degrees. Notice. These guys are at 22.5 degrees. Okay, that's fine. And then I tell them all those. So now I'm going to filter you by 45. So when they come to C, to filter C asks each one, what's your angle? They all answer the same. I'm 22.5.
Okay, but what's the result after C? That's what I want to know.
Wait, so he says, I'm looking for 45 degrees. No one here is 45 degrees. They're all 22. So what's the difference between...
Okay.
So the
I just
difference
want to
is...
know the result from
through
C.
A pass through B, which
he's
means
gonna
15%
say-
are blocked at B, and 15% of those that pass through B are blocked.
It's
Okay,
the same.
so there's nothing
same-
special about this.
For the same reason. No. So, but there seems to be a contradiction between... So this is now, everyone here is at 45 degrees. Everyone here is at 45 degrees. But it's... whatever the number, we don't care about the number here. 15% are blocked, another 15% are blocked. So it's still the majority, whereas here it's 50%. So he's asking, how is 15% plus 50% equal to 50%? It should be 30%.
Oh, I see. That's what he was asking, but that doesn't make any sense to ask that. Oh, he was confusing the crap out of me. Yeah, no, this makes perfect sense. There's nothing strange about this.
I mean,
Like, you don't need anything to do this. Like, this is literally just the magnitudes of the waves. The magnitudes of the components of the waves. Like, there's nothing special about this at all.
What do you mean?
Like, these are just the magnitudes of the components of the waves. Because the 25.5 to 45 is 22.5.
The question is what is bothering him? So you're saying, well, okay, what's the issue? And he's saying, let's hear.
At C. But how on earth does blocking 15% twice add up to the 50% blocked if B is...
No, but
well, nobody says that they add up. These are two different...
See, that's the thing that was confusing me. Like, what the hell? It doesn't make
okay,
any sense. What is he doing? Why is he doing
let
that?
Let me just say something. So he's saying, how does 15% plus 15% equal 50%?
What?
And I'm saying, what do you mean?
Yeah.
Okay, let me just finish a sentence. So he's saying, how does 15% plus 15% equal 50%? And I'm saying it's not. This is a certain conversion, or you can call it a transformation. This is a certain transformation. This is a different transformation. This is like matrix multiplication. Nobody says that you have to end up with the same result. Why would you think that you need to end up with the same result? Like, we can reproduce this in a club. The people walking in, I reassign them numbers, and I'll reproduce this. And if I assign these people this number, I'll reproduce this. This has nothing to do with quantum mechanics. There's nothing to be confused about.
Yeah, I don't understand what's his problem.
Exactly. So let's hear.
Isn't there? Well, it doesn't, which is why the lamp looks a lot brighter when you insert filter B. But it really makes you wonder how the universe is deciding which photons to let you insert.
So he's saying that's the reason filter B makes it look Better, brighter. That's the reason. Okay, so what's the question? Where is there a violation of any known law of physics?
Like this is normal.
This is, I mean, I don't know if it's normal. This is the way quantum particles behave. If you can come up with a different universe, I'll gladly hear about it. But when it comes down to the foundations of the universe, these are the rules. Why are you making so much noise?
Oh, sorry. Like my transformer just fell.
Oh, it's okay. Anyway, let's continue.
if B isn't there? Well, it doesn't.
Look, the point is there's no law of physics being violated, right? I mean, when you read Einstein's paper, they try to make the laws of physics invariant. They want to be invariant to the laws of physics. Okay, we're invariant to the laws of physics. What do you want? Which law of physics did we break? We didn't break any law of known physics. So this is still classical mechanics. This is classical mechanics.
There's nothing
Quantum. I agree. This is a result of quantum mechanics, but there's nothing strange. There's no physics is being violated. There's no violation of any law of physics.
Which is why the lamp looks a lot brighter when you insert filter B. But it really makes you wonder how the universe is.
I wanted to look at it. So yeah, so when you add, yeah, okay, when you add B, it becomes brighter, which is weird. How can you add B and make it brighter? Yeah, it would work just the same in a nightclub. How can you add a filter in a nightclub and get more people? Yeah, that's the way the universe, that's the way it's logic. Once you tell me the rule that whoever passes gets reassigned, we're done. That's it. You signed your fate that instant. 1 second, there's this chick on Telegram. Let me send her a picture. Oh, come on, what just happened? I'm trying to send her a simple picture. Something is wrong with my phone? Okay, forget it.
Whatever.
Yeah, let's continue. You want to continue?
Or we call it a day today.
You want to go?
It's a bit late.
Okay.
Yeah,
you want to go?
Unless you have something related to this, like, do you want to?
No, I don't have anything. We just need to continue, and we need to go into Bell's theorem, but I don't know if this is a good video.
Go a bit into Bell's theorem.
What? You want to go to Bell's theorem?
So we get this out of the way already.
So you want to skip this video and want to go find another video? I agree.
What's the big deal with this video?
Okay, so this is
normal.
What do you mean big deal? We've told you the deal.
Big deal. You showed it.
We showed you. They're going to think this is a big deal.
5 minutes. So
in 1935.
What?
5 minutes so arrogant.
Yeah, EPR paradox and Bell's inequality explained simply in 18 minutes. No, thank you. In 26 minutes.
Today I want to look at what is called Bell's inequality. John.
50 minutes.
Hello. Today I want to look at what is called Bell's inequality. John Stuart Bell, 1964, was responsible for this. It is a response to the Einstein-Podolsky-Rosen paradox, about which I produced a video recently. Now, just to review what that paradox said, what Einstein and Podolsky and Rosen argued, that if you have some kind of system, like energy or a nuclear reaction, whatever it may be, that is responsible for pair production, you might produce, say, an electron and a positron. But what you find by experiment is that if you measure the electron spin, say, against the z-axis, the vertical axis, and you find that the spin is upwards, you might not, you might find it's downwards, but if you find it's upwards, then what you will always find is that the positron spin will be down. In other words, those two spins will always be exactly opposite. Similarly, if you measure the spin along the, say, x-axis, and you find it's in that direction, then were you to measure the spin along the x-axis of the positron, it would always be in the opposite direction. Now, Heisenberg's uncertainty principle says that you cannot know simultaneously both the spin in the z direction and the spin in the x direction. But this appears to suggest that you can, because what could happen is, here is an observer Alice, and here is an observer Bob. And what you can say is that when this electron-positron pair is emitted, Alice will measure the spin in the z direction and find, let's say, that it's vertical. She then shouts across to Bob, I have found a spin in the z direction that is up. If you were to measure your spin, we know that you would find that it's down. But don't do that. Instead, measure your spin in the x direction. And so Bob is supposed to measure a spin in the x direction and find that it's, say, to the right. He would then know that his z direction spin was down and his x direction spin was to the right. He would know both values at the same time. But Heisenberg says he can't. So in practice, what would happen is, if Alice measures the spin in the z direction of this electron, Bob cannot measure the spin in the x direction of the positron. But if Alice doesn't make that measurement, then Bob can make the measurement in the x direction. And the puzzle, the paradox is, how does one particle, how does this positron know whether or not Alice has made a measurement here? And we said,
what do you mean, how does it know? The question is, what's blocking Alice and Bob for measuring both?
there were two possible explanations. One is that the electron and the positron are in constant and immediate communication. No matter how far they fly apart, no matter how far apart they are communicating to one another.
What? I don't understand the question. What did I miss?
In an entangled state, instantaneously, what is going on? But of course, there's a problem with that. That would suggest that information is being passed instantaneously, that is faster than the speed of light. And special relativity says that's not possible. That's what's called a violation of locality. The second explanation is that when these two particles were first produced, when they were born, if you like, they were each embedded with a kind of DNA or hidden variables that would forever govern precisely what they would do in the entirety of their life. And those hidden variables would ensure that they would always remain entangled because that DNA would always govern what they behave.
I'm going to start assuming that there is no faster than light communication.
Yeah, it's better.
Indeed. Now, since it was thought that locality couldn't be violated, in other words, you couldn't have constant communication of an immediate nature because that would violate special relativity, Einstein, Podolsky, and Rosen thought there must be hidden variables embedded in these particles that would dictate what they did. And it was Bell's inequality that...
Sabine Hossenfelder, she believes in super determinism. She believes in hidden variables.
shows that there can't be those hidden variables. Now, to understand how Bell's inequality works, let's first look at the very...
What?
Hidden variables? No, it's not hidden variables. It can't be hidden variables, but it has to be like... it has to be just conservation of energy.
That's hidden variables. Let's listen.
Simple example. We're considering children playing in a playground. Some of them are wearing hats, some of them are wearing scarves, and some of them are wearing gloves. It's a cold day. All of them are at least wearing one of those items of clothing. Some are wearing two, some are wearing all three. And we can represent those children by overlapping circles. They're sometimes called sets. This is set A. This is all the children wearing hats. This is set B, all the children wearing scarves. And this is set C, all the children wearing gloves. Now, where A and B overlap, that's this area here. That means the children are wearing hats and scarves. Where A and C overlap, that's this area here. The children are wearing hats and gloves. Where B and C overlap, that's this area here. That means the children are wearing scarves and gloves. And right in the middle, where A, B, and C all overlap, that means those children are wearing hats, gloves, and scarves. And what Bell's inequality says is that all the people who are wearing hats but not scarves, plus all the people who are wearing scarves but not gloves, is always greater or equal to all the people who are wearing hats but not gloves. And I'll prove that simply by numbering each of the regions. 1, 2, 3, 4, 5, 6, 7. So if you say A not B, well, A not B is region 1 plus region 4. 2 and 5 are part of B. So 1 plus 4 is A not B. What is B not C? Well, B not C is going to be 3 plus 2, because 5 and 6 are part of C. So this is plus 3 plus 2. And that, says Bell, has got to be greater than or equal to A not C. Well, A not C is 1 plus 2, because 4 and 5 are part of C. So now we have that 1 plus 4 plus 3 plus 2 must be greater than 1 plus 2. And that's obviously true, because we've already got 1 plus 2 on this side. Let's put the 1 plus 2 there. Plus 4 plus 3 is greater than or equal to 1 plus 2. Well, it will be equal to if there are no children in categories 4 or 3. But if there are any children in categories 4 or 3, what is 4? 4 is that they are wearing hats and gloves, but not scarves. 3 is that they are wearing scarves, but not hats or gloves. If there's anybody in that, then this equality, or rather inequality, will be true. Incidentally, at this point, I acknowledge Professor Leonard Susskind, who does something very similar to this in his videos on quantum entanglement. Now, how does this help? Well, we need to think about, for example, light.
How is this relevant to
I have no idea what the hell is going.
Yeah.
Why is he showing light? diagrams.
I don't know.
Basic maths of Venn diagrams.
I don't know.
Let's take light, which can be unpolarized. That is to say, the electric and magnetic fields can be oscillating in any direction. You can pass that light through what's called a polarizer. And a polarizer will polarize the light in one direction
Okay, so it has to do with polarization, apparently.
only. Let's suppose that the polarizer will polarize light
I guess ABC is XYZ.
in the up direction, up-down direction. So the light passes through the polarizer and comes out the other side, and it is polarized in the up direction. Well, now let's suppose we take light that's unpolarized, pass it through an up direction polarizer, it comes out the other side polarized. Now we pass it through a polarizer that is exactly at 90 degrees to the vertical polarizer. What will happen? The answer is nothing comes out the other side. But if we took the same unpolarized light, passed it through a polarizer in the vertical direction, and then passed it through a polarizer at the 45-degree angle, some light would come out. Not as much, but some would. And if we then passed that through the polarizer that was, as it were, horizontally polarized, again, some light would come out. Not as much, but some would. So some light gets stopped as you go through this polarizer, more light gets stopped as you go through that polarizer, and more light again gets stopped as you go through that polarizer. But the point is that having gone through a vertical and horizontal polarizer, you still have some light left because you had this polarizer that was at an angle in the middle. Whereas if you'd done it this way, nothing would go through. Well, that's an experiment. You can do that and you can demonstrate it. But now let's look at that from the point of view of an individual photon. Here is a photon that could be polarized in any direction. In practice, of course, it's only...
Yeah, it looks like a violation of logic.
But it's not.
It's not. It's just that's the way photons behave. I mean, yeah. I mean, from
It's
but
actually
we
not
need
a violation of anything. It's actually
we need
perfect
no,
sense.
but we still need to understand it from a quantum mechanical point of view.
It's the same.
But how is this Bell's theorem? I don't understand. Isn't Bell's theorem about entanglement?
We just don't know what it is.
No.
And as it comes to the polarizer, it either will or it won't get through. So it might be part of the photons that get stopped, and it might be part of the photons that get through. Similarly here, a photon comes along. If it gets through this polarizer, that's fine. It's polarized in the vertical direction, but it then definitely won't get through that polarizer. But here's the odd thing. Here comes our self-same photon. It gets through this polarizer and is polarized in the vertical direction. It then gets through, or it may not. There's a probability it will or it won't. It gets through this polarizer. It's then polarized in the angle 45-degree direction. And then when it gets to this polarizer, it might get through or it might not. And if it does, it will be polarized in the horizontal direction. And whether or not it gets through those polarizers is a quantum mechanical phenomena. You cannot predict which of those photons will get through. Some do, and some don't. So now let's try an experiment. And this is an experiment of entanglement. Again, we're going to have some process that produces pair production. In this case, I'm going to use two photons. And they shoot off in opposite directions into the laboratory of Alice and Bob. Experiment. And this is an experiment of entanglement. Again, we're going to have some process.
Finally, entanglement. Let's see.
That produces pair production. In this case, I'm going to use two photons. And they shoot off in opposite directions into the laboratory of Alice and Bob, who are going to have polarizers. And they're going to have just three types of polarizer. One is the polarizer that is vertical, one that is a polarizer at 120 degrees, and one that's a polarizer at 240 degrees. Now, it's important to notice that you cannot predict what the polarization of these two photons will be. It could be in any direction, but if it's pair production, they will be the same. So if you produce two photons, they will have the same polarization. If you then produce another two photons, they will have the same polarization, but not the same as the earlier two, if you see what I mean. So what we're going to do in this experiment is we're going to
Pair production of photons is different than electrons, that the spin is opposite. Rather, whatever their polarization is the same. Okay.
constantly produce pairs of photons. What we know is that each pair will have the same polarization, but the next pair will have a different polarization. And what we're going to do each time we produce a pair is that Alice and Bob are going to randomly select, they've each got these three polarizers, and they're going to randomly select one of them and see if that photon goes through the polarizer or not. Now, according to the Einstein, Podolsky, and Rosen paradox,
Okay, so they're going to violate some rules, let's see.
these photons are supposed to contain hidden variables. That is information that will tell them how to behave whatever circumstances they face. So presumably they must contain information that will tell them whether or not, for certainty, they will go through these polarizers. Because Einstein didn't like the idea of it all being probabilistic. He wanted there to be certainty in all of this. He once said, I like to think that the moon is there, even when I'm not looking at it. There's nothing probabilistic about this. He says, we must know, somebody must know, the photon must know whether it's going to go through these polarizers or not. And that's a hidden...
Wait, you don't have to have hidden variables?
No, there's not.
The problem... Oh, no, you know, for superdeterminism, you have to have hidden variables. Otherwise, they communicate across the universe instantaneously.
Or they change.
Well, this is going to be evidence that there cannot be hidden variables. So let's see the evidence.
Doesn't look good so far.
Doesn't look good to whom?
To me.
To you? No. We look. The universe is plenty flexible. We're gonna get a chance to play with it as much as we want until we figure it out. It's like they say: the criminal can only lose once. The cops can lose as many times as they want. We're the cops. We can lose as many times as we want until we'll crack it. We don't need to get it the first time.
Hidden variable. So one of the hidden variables will be, will you go through polarizer 1, will you go through polarizer 2, and will you go through polarizer 3? And if hidden variables exist, then although we don't know what they are because we haven't discovered them yet, then they must absolutely determine how a photon will behave if it meets one of those polarizers. And we find that there are 8 combinations of this information. We can say that the first combination is, if we take, for example, the 3 polarizers, 1, 2, and 3, we can say that the hidden information may say you can go through all 3. The second option is the hidden information says you can go through 1 and 2, but not 3. The third option is you can go through 1 and 3, but not 2. The fourth possibility is you can go through 1, but not 2 or 3. The fifth possibility is you can't go through 1, but you can go through 2 and 3. The sixth possibility is that you can't go through 1 or 3, but you can go through 2. The seventh possibility
There's a much faster way of doing a truth table. Jesus.
is that you can't go through 1 or 2, but you can go through 3. And the eighth possibility is you can't go through any of them. And those are the only bits of hidden information that could be contained in relation to whether or not those photons will go through any of those 3 polarizers if they happen to encounter them. And don't forget what we said was that every time you do a pair production, you will get a different bit of hidden information. So it won't be the same each time. The first pair production might have this. The second pair production might have this. The third might have this. You don't know. But what you do know is that each of those photons will have the same of those variations because they will both contain the same hidden variables. Now let's look at the experiment which Alice and Bob do. They are each randomly going to pick up one of their polarizers and see if their photon will
There's no point in. Is there a point? Well,
go through it. So the combination could be that A and B, or B and C, or A and C. Now what will happen for each of these 8 variations? Remember, we don't know which hidden information photon we've got. All we can do is do the experiment. Well, what we want to ask ourselves is, when does Alice and Bob get the same information, the same outcome with their photon, and when does it differ? Well, if one has an A and one has a B polarizer, then in each case the photon will go through because its hidden information says it will go through, sorry, it should be not an A and a B, it should be a 1 and a 2, a 2 and a 3, or a 1 and a 3 polarizer. We know that in this, if the photons have this hidden information, they're going to go through 1 and 2, so they'll be the same. They'll go through 2 and 3, so those will be the same, and they'll go through 1 and 3, so those will be the same. This is not very well written, is it? That's 1 and 2, this is 2 and 3, this is 1 and 3. It's the combinations of the polarizers that Alice and Bob have used for the particular pair production that they. I'm going to interrupt myself at this point because having looked at the video, I think I haven't explained it quite as clearly as I would wish. So I'm going to do a kind of an explanation within an explanation and go through a little slower. What we are saying is that we're going to have pair production of photons. Some process is going to generate 2 photons, and those photons will move off in opposite directions into the laboratory of Alice and Bob, who can perform measurements on them. And what we have determined experimentally is that although we don't know what the characteristics of the 2 photons will be in terms of their polarization, they will both have the same polarization. If we do the experiment again, we will generate another 2 photons. Those 2 photons will have the same polarization as each other, but not necessarily the same polarization as the earlier pair. Now, what I've said is that each of them has 3 polarizers. A polarizer that will let a photon through in the vertical direction, in the 120 degree.
We get this right. We're in good shape.
Direction, and in the 240 degree direction. And Alice and Bob are going to randomly select from their polarizers, put them in front of the photon, and they're going to see if the photon goes through or if it doesn't go through. Those are the only 2 options. They can see it go through or it doesn't go through. Of course, there may be occasions where they both pick up the same polarizer. Now, there's no experiment in that at all. We know that if you pick up the same polarizer, the photons will either go through both or go through neither because they're both polarized in exactly the same way. So if they go through if this one will go through a vertical polarizer, so will this one. So any time that Alice and Bob choose the same orientation of polarizer, we can ignore that experimental result because that's bound to be the case. We already know that's the case. It's only when Alice and Bob pick up different polarizers that you get information. And what we want to record for each experiment, every time we do a pair production, we're going to do this experiment where Alice and Bob randomly select from their 3 polarizers and see whether the photon goes through. The question we want to ask is, do they get the same result or a different result? Now, a same result means that the photon goes through both polarizers, or the photon goes through neither polarizer. A same result is they both go through or neither go through. A different result means that a photon will go through one polarizer, but not the other one. I hope that makes what follows a little easier to understand. So now let's look at this one. If you have polarizers 1 and 2, then you'll get the same outcome. If you have 2 and 3, you'll get a different outcome because the photon will go through 2, but the photon won't go through 3. Similarly for 1 and, this is 1 and 3, let's scrub that out, 1 and 3. For 1 and 3, you'll get different. If you come down here, for 1 and 2, you get different. From 2 and 3, you get different. 1 and 3, you get the same.
What is he saying? What's going on here?
I mean, he's doing this in a very stupid way. That's what he's doing.
So Alice and Bob, if they pick up the same filter, then they'll get the same result. If they pick up different filters, but they'll get different results? I don't get it.
I don't know why he's doing it like this. It's just kind of crazy.
I don't understand. Alice and Bob, I mean, the filters are not even 90 degrees to each other, so it's like they might be because they're different, but they're different angles. So So the question is, do they pick up the same filter or a different filter? And what is he saying here? Like case 1, what is 1, 2, and 3? They pick up the same one. In case 1, what is 1, 2, and 3? There's 3 filters, but Alice picks 1, Bob picks 2, and what is 3? These are all the combinations. What do you mean combinations? But you can only use 2 filters. So what do you mean? I don't get it. What combination?
Doesn't make any sense, to be honest.
Figure this out. Everything until the Alice and Bob experiment, everything was very. I mean, once you say entanglement, no, you can say hidden. He's trying to disprove hidden variables. That's the trick.
It's doing dumb shit. That's the trick.
Might get through, or it might not. And if it does, it will be polarized in the horizontal direction. And whether or not it gets through those polarizers is a quantum mechanical phenomenon. You cannot predict which of those photons will get through. Some do, and some don't. So now let's try an experiment. And this is an experiment of entanglement. Again, we're going to have some process that produces pair production. In this case, I'm going to produce 2 photons. And they shoot off in opposite directions into the laboratory of Alice and Bob, who are going to have polarizers. And they're going to have just 3 types of polarizer. One is the polarizer that is vertical, one that is a polarizer at 120 degrees, and one that's a polarizer at 240 degrees. Now, it's important to notice that you cannot predict what the polarization of these 2 photons will be. It could be in any direction, but if it's pair production, they will be the same. So if you produce 2 photons, they will have the same polarization. If you then produce another 2 photons, they will have the same polarization, but not the same as the earlier 2, if you see what I mean. So what we're going to do in this experiment is we're going to constantly produce pairs of photons. What we know is that each pair will have the same polarization, but the next pair will have a different polarization. What we're going to do, each time we produce a pair, is that Alice and Bob are going to randomly select, they've each got these 3 polarizers, and they're going to randomly select one of them and see if that photon goes through the polarizer or not. Now, according to the Einstein-Podolsky and Rosen paradox, these photons are supposed to contain hidden variables. That is information that will tell them how to behave whatever circumstances they face. So presumably they must contain information that will tell them whether or not, for certainty, they will go through these polarizers. Because Einstein didn't like the idea of it all being probabilistic. He wanted there to be certainty in all of this. He once said, I like to think that the moon is there, even when I'm not looking at it. There's nothing probabilistic about this. He says, we must know, somebody must know, the photon must know whether it's going to go through these polarizers or not, and that's a hidden variable. So one of the hidden variables will be, will you go through polarizer 1, will you go through polarizer 2, and will you go through polarizer 3? And if hidden variables exist, then although we don't know what they are because we haven't discovered them yet, then they must absolutely determine how a photon will behave if it meets one of those polarizers. And we find that there are 8 combinations of this information.
I don't get it. I don't understand. So you create a photon pair. You create 2 photons that are both polarized in the same direction. Both are either up or down, left or right, whatever they are, they're both the same. Which makes sense because they both came out of the same electron. Let's say they both came out of the same electron. So the same motion created these 2 photons.
Yeah.
Okay, so they are entangled. But because of the limitation of quantum mechanics, they can only be measured in a certain... You can only measure them at a certain direction. Whatever it is, what you'll get the same, you must get the same result. Let's say it's, I mean, if they're both up and down, then this will pass. If you apply this filter and they're both up and down, no problem. But what if they're both up and down and you apply this filter? Then do we expect them to get the same results? Because they're each 50%. You understand?
Yeah, I do. But
what?
Yeah,
so
we should get, in this case, you should get 0 if you apply the
No. Let's say the photons are both moving up and down. So filter 2 should give us, let's say, 50%. The photons are both moving up and down. The filter is at 45 degrees. So the answer is 50%. The question is, should Alice and Bob both get 50%, or should Alice and Bob each get 50%, which means sometimes they'll get the same answer, but other times they'll get different answers because it's 50%. Each one is flipping 50% coin.
Hmm?
You understand the question? You're not listening? Your audio is completely shite. You're roboting. Can you hear me? Can you hear me? Can you hear me? Okay, you're back.
Oh, yeah, I'm back.
So my question is very good. The question is, what do we expect?
Oh, are you there?
I'm here, yeah, I'm here. 1, 2, 3, 4, 5. So you don't have internet. I'm assuming you don't have internet.
Oh, I mean, it went down again for a while. I don't know what you're saying. Whoa,
You don't
that's a lot of
have
things.
internet. So I'm assuming you don't have internet.
I have.
You have?
I'm
So
here
are you
already.
able to? You what?
Yeah, I think. Yeah, it's probably fine.
Okay, so the question is like this. So Alice and Bob created two photons, or two photons were created that are of the same polarization, right? Because the same electron motion created both photons.
Yeah.
So they're polarized exactly the same way. So they are entangled. They both, one flies to Alice, another one flies to Bob. Now, let's say the photon is moving up and down. It's polarized up and down. So that if Alice and Bob used filter 1, they would
My
both
cat is
get...
here.
What?
My cat is here calling.
I can't hear you.
Oh, I got distracted because my cat is here calling.
Your cat has an inner ear colon?
No,
And
he's just calling me.
oh, well, cat is very important. But tell the cat we're gonna treat it, we're gonna give it the Schrodinger's cat treatment.
No.
Okay. All right. So the question is, listen to the question.
Okay.
So you have an electron moving up and down. Therefore, you have two photons created with the up and down polarization. Same polarization, okay?
Mm.
Yes or no? Because this is the 4th time, 10th time I'm explaining this. You gotta be with me.
Sorry.
You want to go to sleep? What do you want to do? I cannot explain this again and again and again.
So
It's
yeah,
too much.
they will. I mean, in this case. So in this case, they will. Yeah, they will have the same polarization.
Yes, that's a given. So this is a machine that creates two photons with the same polarization. I'm just saying they have a shared electron that's moving up and down, and it's creating always the up and down polarized light. Okay?
Yeah.
Yeah.
So far,
What? Yeah. Am I talking to myself again?
No. So far, so good.
Okay, so the same polarized light goes to Alice up and down, goes to Bob up and down. Now, if Alice and Bob used filter 1, then they would both get what percent?
If they both use filter 1,
Filter 1.
I mean, they get what percent? I mean, if it's polarized up, they will get 100%.
Yeah, so they will. If they use filter 1, they will both get 100%. But what if they both use filter 2?
Well, if they both use filter 2, they will both get 50%.
Right, but that means each flips a coin. they don't get the same result. They both
They
get
get
50. What?
Oh, if it's only one photon, they flip a coin.
No. This is one photon goes to Alice, a different photon goes to Bob, but these two photons are entangled. They just have the same polarization. If they both use filter 1, they both get pass. If they both use filter 2, they both get 50%. But that means they each flip a coin 50%. It doesn't mean they both get true or false. They just both get.
If they're entangled, they supposedly one gets true and the other gets false.
No.
No, if they're
No,
entangled,
they both get. No, you could say they both get true. They both must get the same result.
No, I think if they're entangled, it's gonna get to the point where they both get if one gets true, the other gets false.
No, this is not electrons with the up and down.
It probably work that way, but let's see.
No, this is not electrons. He explained. They are the same polarization. Whatever polarization A gets, B also.
Oh, exactly. That's true. That's true.
But the question is, what if they use the wrong filter? What if they use filter 2? Do we expect them to get the same result?
Yeah.
Yeah, what?
Yes.
How do you know?
I don't know, but I think yes.
We don't know. We don't know how quantum physics works, and we can never know. How can we ever know the answer to this question?
We don't
know.
Test it.
No, you can't.
Let's see what he says. Let's see what he says.
So you're right. No. So in order to test it, you have to start with light that you know exactly how it's polarized. So let's say it's purely up and down. And then you have to run a bunch of tests. And Alice and Bob should use the same filter, and they should get either they will always get the same result. Well, we don't know how it works. He never explained to us how it works. This was never told to us. Let's go back.
Experiment of entanglement. Again, we're going to have some process that produces pair production. In this case, I'm going to produce two photons, and they shoot off in opposite directions into the laboratory of Alice and Bob, who are going to have polarizers. And they're going to have just three types of polarizer. One is the polarizer that is vertical, one that is a polarizer at 120 degrees, and one that's a polarizer at 240 degrees. Now, it's important to notice that you cannot predict what the polarization of these two photons will be. It could be in any direction, but if it's pair production, they will be the same. So if you produce two photons, they will have the same polarization. If you then produce another two photons, they will have the same polarization, but not the same as the earlier two, if you see what I mean. So what we're going to do in this experiment is we're going to constantly produce pairs of photons. What we know is that each pair will have the same polarization, but the next pair will have a different polarization. And what we're going to do each time we produce a pair is that Alice and Bob are going to randomly select, they've each got these three polarizers, and they're going to randomly select one of them and see if that photon goes through the polarizer or not. Now, according to the Einstein, Podolsky, and Rosen paradox, these photons are supposed to contain hidden variables. That is information that will tell them how to behave whatever circumstances they face. So presumably they must contain information that will tell them whether or not, for certainty, they will go through these polarizers. Because Einstein didn't like the idea of it all being probabilistic. He wanted there to be certainty in all of this. He once said, I like to think that the moon is there, even when I'm not looking at it. There's nothing probabilistic about this. He says, we must know, somebody must know, the photon must know whether it's going to go through these polarizers or not. And that's a hidden variable. So one of the hidden variables...
So the photon has to know what is going to be the polarizer, and it has to know whether to pass or to fail. This doesn't make any sense. Are you there? Are you listening, or are you sleeping?
Yes, I'm listening.
So I don't understand where we're at this point. So
no,
we started.
Let him go. Just let him keep going.
What do you mean? I don't understand the question. What do you mean let him go? We already listened all the way to here, and then this. I don't know what's going on. I don't know what's going on. I don't understand where we're heading. I don't know what's the question at this point.
The question
I don't care, and I don't care what Einstein liked or didn't like. The question is, if you have, right, let's go back to the beginning. Let's go
No.
back all the way to the beginning, all the way to
Hello.
the
Today I
beginning.
want to look at what is called Bell's inequality. John Stuart Bell, 1964, was
I
responsible
mean,
for this.
I
It
don't
is a
have time
response
to
to.
go to the beginning today.
No, I don't need to go to the beginning and listen to the whole thing. I'm lost. I don't know what the question is at this point.
Wait.
What?
Yeah, you can keep going, but I got a problem to solve here.
What are you working on? Oh, work?
To the Einstein-Podolsky-Rosen paradox, about which I produced a video recently. Now, just to review what that paradox said, what Einstein and Podolsky and Rosen argued that if you have some kind of system, like energy or a nuclear reaction, whatever it may be, that is responsible for pair production, you might produce, say, an electron and a positron. But what you find by experiment is that if you measure the electron spin, say, against the z-axis, the vertical axis, and you find that the spin is upwards, you might not, you might find it's downwards, but if you find it's upwards, then what you will always find is that the positron spin will be down. In other words, those two spins will always be exactly opposite. Similarly, if you measure the spin along the, say, x-axis, and you find it's in that direction, then were you to measure the spin along the x-axis of the positron,
I don't understand this part of the video either.
it would always be in the opposite direction. Now, Heisenberg's uncertainty principle says that you cannot know simultaneously both the spin in the z direction and the spin in the x direction. But this appears to suggest that
This is not simultaneous. Oh, but you're going to end up knowing it's simultaneous. Okay.
you can, because what would happen is, here is an observer Alice, and here is an observer Bob.
And why did Heisenberg say this? That you cannot know it in two directions? Why? Why? What is that a violation of?
And what you can say is that when this electron-positron pair is emitted, Alice will measure the spin in the z direction and find, let's say, that it's vertical. She then shouts across to Bob, I have found a spin in the z direction that is up. If you were to measure your spin, we know that you would find that it's down. But don't do that. Instead, measure your spin in the x direction. And so Bob is supposed to measure a spin in the x direction and find that it's, say, to the right. He would then know that his z direction spin was down and his x direction spin was to the right. He would know both values at the same time. But Heisenberg says he can't. So in practice, what would happen is, if Alice measures the spin in the z direction of this electron, Bob cannot measure the spin in the x direction of the positron.
What do you mean cannot? What do you mean cannot? I don't know what it means cannot. Who's going to stop him? What is this nonsense? I don't understand what's going on.
Yeah.
I don't know what it means he
He's
cannot.
explaining a bunch of assumptions.
What?
He's not explaining a lot of assumptions.
Okay. So there's no point. Okay, so there's no point in listening to this video. This is a 26-minute video, and it's not explained properly. It's useless. So if in 20 and this guy is one of the best explainers I know. So it's useless. It's hopeless. Let's see Bell's theorem.
Hey everyone, welcome to this next.
No, not
everyone.
50
Welcome to this
minutes.
next episode.
What?
That has 50 minutes. That's a 50 minutes video.
Fine. Look, I don't know what to say. I mean, we have to study this. So you want to go to sleep?
But it has to be tomorrow. Okay.
No problem. No. When are you available?
Maybe late in the afternoon. I don't know. I will see.
Okay. Okay. Text me when you're ready. All right.
I
Bye.
think I know where he was going. I think he was just going to make like the truth table to see if there are hidden variables or not.
It's useless. It's useless. I don't understand the question. I don't care what the answer is if I cannot answer the question, then what's the point in listening to his answer? This guy lives in such terrible look at how he lives. Unless it's his basement, what kind of life is this? This guy is making probably a million.
Looks like a very nice basement.
What kind of a life is this? He's making like $1 million a year. He can't live in a normal house? What kind of a life is this?
It doesn't look bad.
Maybe
Why?
he lives probably in the suburbs in New Jersey or something. All right. Anyway, go to sleep. I'll talk to you tomorrow. I'll keep going. I'll listen. See you. Bye. Okay. I'm going to keep going. Let's try and listen.
Episode of your daily equation. And today I'm going to take up a result that some physicists, some commentators have described as the most profound result in theoretical and experimental physics. I'm not sure I would agree with it as the most profound, but without a doubt, it ranks among the top few of the most remarkable, most surprising insights that have emerged, say, in the last 100, 150 years. So it's well worth spending a little time thinking about it. And the topic that we're focusing upon is the possibility that our world allows for influences that are non-local. What does that mean? A non-local influence. What's a local influence? Well, that's an ordinary influence. And you do something, whatever. You snap your fingers, you clap your hands, you push something, you move something around, and the influence that you exert manifests in your local environment. It's unusual to imagine that you could say punch your fist forward and like hit somebody in the back of the head or in the nose on the other side of the country. I don't sort of like that violent metaphor, but
no, what he means is violation of the speed of light. I think that's non-locality. Locality just means you're violating the speed of light. That's all.
But you sort of get the gist. What you do according to logical reasoning, what you do according to everyday experience, what you do according to the laws of physics, as we thought we understood them prior to what I'm going to talk about here today, what you do here influences things here. It doesn't influence things instantaneously or immediately someplace far away from here.
Locality just means violation of the speed of light. I don't know why they confuse people with nonsense.
Here. So locality is you exert influence, it affects your local environment. Non-locality is the possibility that you exert some kind of influence and it affects something far away. And it
No. And it influences and you violate the speed of light. That's all.
It was the insight of a variety of individuals. We'll talk about a number of them today, but let me bring them up on the screen. Albert Einstein right here played an absolutely essential role in the story that I'm going to describe here because it was his insight, together with two colleagues, I'll show you them in a moment, Podolsky and Rosen, that came up with an idea that ultimately rippled through our understanding of physics, giving us a radically different picture than even Albert Einstein would have anticipated. And this relies upon a variety of ideas having to do with quantum mechanics, quantum entanglement. The culminating effort in this direction emerges with this guy over here, who among physicists is extraordinarily well known. For the general public, less well known. This is John Bell, an Irish physicist, who, as we will see, was able to take a completely abstract, theoretical idea, almost a metaphysical idea, at least it seemed metaphysical in the sense that it didn't seem to have any experimental consequences that Einstein and his colleagues came up with. And Bell was able to show that Einstein's idea was not metaphysics, that Einstein's idea was physics, which meant Einstein's idea could be tested. Indeed, as we'll see, he wrote down the test. And later on, physicists came along and carried out that test to profound effect. Okay, so here are the three main culprits in the story: Einstein, Boris Podolsky, and Nathan Rosen. And it was in 1935 that they wrote this paper over here. And you may, if you've been following the series, you'll note that in the episode on quantum entanglement, I don't know what episode it was. You don't have to have watched that episode to understand the discussion here today, but it would help if you looked at that. So in that episode, I described the basic idea of entanglement and the basic conclusion of the paper that Einstein and his colleagues wrote here. But I'll remind you of that again and again. The overarching implication or the overarching message of Einstein's paper with these two colleagues was not that quantum mechanics was wrong. So this headline in the New York Times really is spot on. Scientists and two colleagues find that quantum mechanics is not complete, even though it is correct. So Einstein and Podolsky and Rosen were never saying that quantum mechanics is wrong in the sense that it makes predictions that are in conflict with observation or experiment. What they were saying instead was the view of reality that quantum mechanics puts forward is an incomplete description of reality. And Einstein and his colleagues were arguing that there has to be a deeper description, even though they were unable to give that deeper description. They believed that in this paper they had established that there was a deeper description waiting to be found. And their analysis relied on this idea of quantum entanglement, which pictorially is this idea that you can have two particles that can be widely separated, and yet there's still a kind of quantum mechanical thread, an invisible thread. I show here in yellow just to sort of give it a little visualization. But it's as if there's an invisible quantum mechanical connection that links these two particles regardless of how far apart they are, and allows it to be the case, according to standard quantum mechanics, that if you do something to one of these particles.
Why is your particle so weird? A particle should be just a wave. Yeah, but I guess it could be a really bizarre wave. But you can see that it's inside the ether. So even in his mind, where there is no ether, there's still ether. Everything is waving.
Particle, say the one on the right, it can have an immediate influence on a measurement on the particle on the left of the image, even though they might be miles, kilometers, light years apart. That is very strange. And this is why Einstein called this spooky, right? It was a spooky implication of bread and butter quantum mechanics, that you could set up two particles in this manner such that you perform a measurement on one of those particles and it immediately, instantaneously has an impact on a measurement undertaken on the partner particle, regardless of how far apart. I mean, that's crazy sounding talk, right? But yet that's what standard quantum mechanics seem to be implying. And Einstein and his colleagues came along and said,
there's no violation in what you just said. You're not saying that what I'm doing here implies or affects what happens somewhere else. You're saying it impacts the test results that are done somewhere else. That's different. That's not action reaction. It's a little bit different. So you have to be careful with what you're saying. No one says that my action leads to some reaction somewhere else. My test here, my quantum mechanical test here, implies some quantum mechanical test result somewhere else. Or my quantum mechanical test result here implies an instantaneous quantum mechanical test result somewhere else. That's okay. It's still incredible, yes. That there seems to be instantaneous communication. Yeah, that's unacceptable. That's magic.
We don't buy that. We believe there's a different picture, and I'll show you what the picture is that Einstein, Podolsky, and Rosen put forward. And that picture is ultimately what John Bell analyzed and showed that that new picture could actually be subject to experimental test. And as we'll see, the way in which Einstein and his colleagues envisioned the world behaving is not actually borne out by the experiment. It's not fully refuted, as some say, and I'm going to come to that subtlety toward the very end. But the image that Einstein had of a world in which influences would be local seems not to be our reality. It seems to be the case, and I'm hedging my description only because at the end I'll describe one or two potential loopholes in this conclusion. But the most straightforward reading of the discussion that I'm going to have here now is that our quantum mechanical world does allow this kind of non-locality. It does allow a measurement in one location to have an influence on a measurement taking place at a distant location, regardless of how far apart they are. All right, so I'm not going to follow the precise way in which Einstein and his colleagues came to this conclusion. Instead, I'm going to use the same kind of example that I used in the discussion earlier of quantum entanglement, that earlier episode, which makes use of this property of particles called spin, quantum mechanical spin. Now, not everybody's familiar with quantum mechanical spin. Roughly speaking, for the purposes that we have at hand here, you can think about it as follows. Particles have a quality that allows you to think about them as if they're spinning around like a top. And any given species of particle has a fixed amount of this quantum mechanical spin. The Higgs boson was so special because it has none of this quantum mechanical spin. It's the first particle that we've ever encountered that doesn't have a certain amount of spin. It does have a certain amount. It's zero in that particular case. But electrons and quarks and the familiar matter particles have an amount of quantum mechanical spin called spin 1/2. All that means pictorially, which is fine for what we're discussing here, is this. So you can have a particle, and I kind of hope you can see this. This particle is actually spinning around. Get close to your screen if you don't see it. Yeah, I think you can probably see it. So it's spinning around. In this particular case, it's going in a clockwise orientation. The particle can also spin around this axis the other direction, the same amount, roughly speaking, the same speed of spin, if you will. And we have an arrow that we could point directly in the direction of the spin, as in this particular case here, the orange arrow, or the other direction, we can have this purple arrow going, say, in this counterclockwise direction. It's really awkward to try to have arrows that spin around with the particle, so we use different notation. So for this case, instead of having the arrow going around with the particle, we say that the particle is spinning up, which is just the right-hand rule. Take your fingers, you curl it in the direction of the spin, and your thumb points in the direction that we use to describe that kind of spinning motion. So in this case, counterclockwise spinning up, and the opposite would be spinning down. And again, you have to get really close to see it, but that particle is spinning around in this clockwise direction, which by this right-hand rule would be spinning down. Now, the weirdness of quantum mechanics really comes to the fore when we realize that quantum mechanics allows a particle to be in kind of a fuzzy mixture of both spinning up and spinning down at the same time. It's hard to show that pictorially, but take a look at this, right? So this is not a really good depiction, but it gives you a rough sense that it's kind of up and down. The problem with this imagery is at any given moment, if I was to stop this animation, the arrow would be up or it would be down, which would mean at a given moment it had one or the other spin. That's not what quantum mechanics tells us. Quantum mechanics tells us that the particle is in a mixture of both spins at the same time. So I can't really depict that, but this is sort of, not a bad visual image, visual metaphor to have in mind. And only when you measure the particle does it snap to attention and acquire a single definite spin. In this case, it snapped to attention spinning in the upward direction. But if this is a 50-50 mixture, half probability of up, half probability of down, then if I measure it again, it could be up or down, 50-50 chance.
So the way I view it is that the particle is a wave, and a wave doesn't have spin. But when you measure the spin, it collapses, or it shrivels. So the wave is very big. When you interact with it, it shrivels into a tiny wave. And then it does have a spin. So like an electron as a wave, you cannot see the spin. You simply cannot see the spin. It's way too big. But then when the electron ends up hooking up with a proton, that it goes into a tiny space, and then the spin comes out. Then you can measure its spin. That's the only time you should be able to measure the spin of an electron. Like when they do the Stern-Gerlach, so there is an electron at the outer shell of a silver atom. That means that electron is confined into a relatively tiny space, and like a femtometer space or something. So then the spin comes out. So I would say the spin is always there, because the universe is mechanical. So the spin of the electron is always has been there. When the electron travels through the Higgs field, I think it gets bounced back and forth, and it keeps changing its spin. It's they call it chilarity, chilarity. I don't remember. Anyway, but the interaction with the Higgs makes it change its spin back and forth as it's bouncing through the Higgs field. So, but then it's not confined. But every interaction with the Higgs field maybe makes it shrivel. I don't know. And then when it goes and wraps itself around some atom, then its spin is measurable. So much so that when you fire the atom through the non-uniform magnetic field, it either goes up or down because of the spin, because of the way it's spinning. It's not spinning around itself. It's spinning around the protons, the nucleus. It's spinning around the nucleus in a certain direction. I don't know how that works. Bohr said that it's spinning. It's orbiting. It has an orbit with a certain direction. I don't know. I don't know how it works. I don't know if anyone knows how it works. We still don't have a mechanical explanation of how it works. So anyway, where were we? Let's listen.
But if this is a 50-50 mixture, half probability of up, half probability of down, then if I measure it again, it could be up or down, 50-50 chance. And in this particular animation, it turned out that that's...
So we don't know, but because it's bouncing through back and forth in the Higgs, it keeps changing. The question is, so they say, anytime you measure it, you're going to get the opposite for the other electron, for the positron? Why? Why would that be the case? How? It's bouncing back and forth. I don't know. I don't understand it.
Second measurement gives this particle spinning in the downward direction. So it's weird, very strange. Quantum mechanics allowing this sort of fuzzy, nebulous reality until a measurement or an interaction takes place, which forces that reality to ante up and choose one or the other outcome. In this particular case, only two possible outcomes. The particle chooses one or the other only when the particle is confronted by a measurement or confronted by an appropriate interaction that disambiguates this blending of possibilities, which is the reality prior to that interaction. So totally strange, but this is the standard part of quantum mechanics. It's got weirdness in its own right, but now we go further. And the weirdness of quantum entanglement as applied to this particular example of quantum mechanically spinning particles is this. According to quantum mechanics, you can set up a situation where you have two particles, each of which is in this fuzzy mixture spinning up and down at the same time, but you can set it up so that their spins are correlated, so that they're both in a 50-50 mixture up and down, but the spin of one is opposite to the spin of the other, in the sense that if you were to set up this situation, they're both sort of 50 up, 50 down. Let's say you go to the particle on the right, you measure it, it snaps out of the haze, purple pointing up, and the particle on the left, or at least my left, is pointing down. I always get confused if your left and my left will be the same. So I hope that what I'm calling right and left is not reversed, but be that as it may. The purple one is spinning up and the orange one is spinning down. And the curious feature of this is I only interacted with the purple particle, this is the one that turned out to be purple, and it forced the other particle to disambiguate and spin down once the one that turned out to be spinning up acquired that definite spin. That's the weirdness of quantum entanglement, because these two particles could be arbitrarily far apart. And an image that makes this a little bit more dramatic. Again, it's schematic, but it's more energetic, if you will. Here are two entangled particles in this 50-50 mixture spinning up and spinning down. I go to the particle on the right and I measure it, it spins down. Immediately, the one on the left snaps out of the haze and spins up. Again, I can do this again. They're 50-50 mixture up and down. Let's say I go to the particle on the left and I measure it and snaps out of the haze, spinning down. The one on the right will snap out of the haze instantaneously, spinning the opposite orientation. And that is the weirdness of quantum entanglement. And that's the spookiness of it, right? I mean, how could it be that you measure one and it affects the other? So what does Einstein do? Well, let me show you what he does.
So how do you know this? Was there an experiment done that does this, that confirmed this? Because I just learned that the Higgs causes the spinning to switch back and forth. So why would these two particles ever give the same results? Sounds like it depends on the Higgs interaction. I mean, what is this based on? I don't have enough information.
Does in the context of taking these abstract examples of spinning particles, let me put them into more of a laboratory setting. Okay, so in a laboratory setting, we can imagine that we have, say, a couple of detectors, and one detector on the right, one detector on the left, and in the middle is a device, if you will, that will send out particles that are entangled. So this device in the middle creates entangled particles, and it creates them in just the way that we've been describing. One up, one down, the other up, the other down, and so forth. And these detectors are able to measure the spins of the particles. So the example that I was just showing you a second ago.
It's always illustrations. It's never actual equipment. I don't know what's wrong with these people.
In this language would look like this. Two particles, say, are emitted from the center device. They're both in the mixture up and down, and then they get measured on the left and the right. And when they're measured, one is up, one's down, or in the reverse case, the other's down, the other's up, and so forth.
Okay, I'm done. I'm gonna go to sleep. All right, let's stop here. ASL, thank you very much for your note. All right, everyone. See you tomorrow. Bye.